So now that we understand the process of identifying the nodes in a circuit, we can write equations for each of those nodes. Before we talk about writing those equations, let's just take a minute and consider why would we need a new tool? Why is it that nodal analysis is so important and so powerful if I'm telling you that we've already seen all of these other tools? We've seen resistors in series, resistors in parallel, voltage division, current division, Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law. You're a master at all of those rules. And yet you still can't solve the circuit that's shown in figure 2. Because there isn't a pair of resistors that are in series or in parallel in this circuit. Now, could you solve this? Yes. You could write a Kirchhoff's current law right here. You could write a Kirchhoff's current law right here. You might need to write a Kirchhoff's current law at the top. Ultimately, you'd have to solve those all simultaneously. But it would be very unstructured, and it would be very difficult to figure out where you're supposed to write the equations and how you're supposed to write the equations. What we need is a structured, step-by-step method that is guaranteed to be able to solve any circuit's problem. Well, maybe I don't want to say any circuit's problem. Any circuit's problem that involves current sources, voltage sources, and resistors. I think that's fair to say. And at this point, we need to see that tool because this circuit shown in figure 2 is beyond the current scope of our abilities. So, can we identify the nodes in this circuit? Sure, that's no problem. There's a node across the top, there's a node here in the middle, there's a node over here on the right, and then there's a node across the bottom. That node across the bottom, by the way, is the reference node. Remember that the reference node is always going to have a voltage of 0. So we know the voltage at the bottom node is 0, but we don't know the voltage at the top node or in the middle node or on the right-hand side. We'd really like to know those voltages. Those are known as node voltages, and the whole purpose of nodal analysis is to calculate those voltages. Now you might say, there must be some fancy new equation that we're going to be using to write these nodal analysis equations. Nope. It is strictly Kirchhoff's current law. You're going to be writing Kirchhoff's current law at every node, but you're going to do it in a special way where you're summing the currents leaving the node. Now we could do it in other ways. We could sum the currents entering the node. We could set the currents entering equal to the currents leaving. But by summing the currents leaving the node, we're going to end up with a very particular structure of the matrix that is going to be very easy for us to identify as being correct. So the first step is to identify each of the nodes. Here you can see that I've identified each of those nodes. So I have V1, V2, V3, and then across the bottom of the circuit I have V0. So that was the subject of the previous video. I'm confident that you can identify the nodes. The next step is to write a Kirchhoff's current law at each unknown node. Let me clarify again. Let me verify that you do not write Kirchhoff's current law at the reference node. If you try to write Kirchhoff's current law at the reference node, you're going to end up with a 4x4 set of equations. Rather than 3 variables with 3 equations with 3 unknowns, you'll have 4 equations with 4 unknowns, but they won't be independent of each other. You'll end up with a matrix or with a set of equations that are dependent. And this means that you'll not be able to invert the matrix. It will end up being that it is a singular matrix. And this means that MATLAB or your calculator will fail to invert it. How do I know this? I lost so many hours of sleep when I was a sophomore because I forgot to note the fact that the reference node has a voltage of 0 volts. We had a big final project, and I probably spent 40 hours programming that project when it should have been about 3 because I couldn't debug it. I couldn't figure out why my matrices were coming back singular, and so it's really been pounded into my head. Don't forget V0. Don't write an equation. Okay, so we're going to write an equation. The sum of the currents leaving is equal to 0 for each of the other nodes, for each of the unknown nodes. Now, I've redrawn figure 3, and I've identified some extra currents. Notice that I have I sub 2, 1 and I sub 1, 2. You might say, why do you need both of those? Each of them is going to be valuable in one equation and not in another equation. But the key to realize here is that those two subscripts, the first subscript is the source of the current, and then the second subscript is the destination. So here you can see this current is going from node 2, so it's V2, therefore it's node number 2. It's going to node V1 or node 1. So the source is node 2, the destination is node 1, so it's I sub 2, 1. But I sub 1, 2 has V1 as the source and V2 as the destination. So when you flip those two subscripts, you're going to reverse the direction of the current. Over here, I sub 3, 1 is going from node 3 to node 1. I sub 1, 3 is going from node 1 to node 3. And then here we don't need the reverse of these two currents, but in both cases we're going from node 2 or 3 down to node 0. The other thing to know is that I need the current that's leaving each node, and although this current source is entering the node, I'm just going to, for clarity, rewrite it as a negative current that's leaving the node. That'll just make our lives a little bit easier as we're writing the Kirchhoff's current laws. Okay, consider Kirchhoff's current law for the top node. I see that negative I sub s is leaving because positive I sub s is entering. I see I sub 1, 2 is leaving, and I see I sub 1, 3 is leaving. So I can write I sub 1, 2 plus I sub 1, 3 minus I sub s equals 0. At node 2, I see that I sub 2, 1 is leaving, I sub 2, 0 is leaving, and although I didn't remember to put an arrow in here, it's I sub 2, 3 is leaving. So you can see here I sub 2, 1 plus I sub 2, 3 plus I sub 2, 0 equals 0. And then at node 3, we have I sub 3, 1 is leaving, I sub 3, 2 is leaving, and I sub 3, 0 is leaving. And so we add those three together, and they're equal to 0. Equations 2, 3, and 4, that's the heart of nodal analysis. It is not yet in a form that is very useful to us, but that's Kirchhoff's current laws. And we know that Kirchhoff's current laws are true, so therefore these three equations are true. But now we need to rewrite each of these currents, except for I sub s, that'll just be a constant. But each of the other currents, we need to write them in terms of node voltages. So let's take I sub 1, 2 as an example. If I come back up here, I sub 1, 2 is this current right here. It's flowing between node V1 and node V2. This means that it's going to have, but by the passive sign convention, it will be more positive on V1 and more negative on V2. So you could say that the voltage here is V1 minus V2. And voltage divided by resistance will give you current. So V1 minus V2 over R1 will give you I2. So we use Kirchhoff's current law first to write a set of three equations. And now we're going to use Ohm's law to replace each element of those three equations. So I sub 1, 2 is V1 minus V2 over R1. Notice that the subscripts 1 and 2 match these subscripts 1 and 2 because they have to be the source and the destination. You have to look on the circuit diagram to figure out which resistor goes here. But if I scroll back up here, you can see that between nodes 1 and 2 is the resistor R1. So you have to look at the circuit diagram to figure out which resistance goes in each denominator. So we're going to go ahead and substitute each of those currents are going to be substituted by a voltage difference divided by a resistance. And you really have to be looking at the circuit diagram to be able to do each of those conversions. Notice that in two of these cases I have a V0, so V2 minus V0 over R4, V3 minus V0 over R5. V0 is known to be 0 volts, so I just mark it out of the equation. I don't need it anymore. I'm going to go ahead and move the I sub s over to the other side, and I'm going to group the terms that correspond to V1 and V2 and V3. So essentially all I've done is to rewrite this equation where I've just lumped together V1 times 1 over R1 plus V1 times 1 over R2. So you can see I've lumped that together. I have V2 times minus 1 over R1 and V3 times minus 1 over R2. And then I move the I sub s over to the right-hand side. So equations 9, 10, and 11 are really just an alternative representation of equations 6, 7, and 8. Now, if you notice, I have V1, V2, V3 constant. V1, V2, V3 constant. V1, V2, V3 constant. This is the perfect representation for a matrix form. So I'm going to rewrite this equation in matrix form, where I simply take each one of these coefficients and I put them as matrix elements. It'll be a 3 by 3 matrix, so I need 9 coefficients. And then the right-hand sides, I sub s, 0 and 0, that forms the right-hand side column vector. And then there will be a column vector which contains the unknown variables, V1, V2, V3. That's going to be multiplying times the matrix. Once we get into this form, we can now tackle solving this equation in one of several ways. MATLAB is very powerful, can be used. The mat in MATLAB comes from matrix, so it's very good at doing matrix inversions. Or we could use our calculators. The RREF, the reduced row echelon format, is a powerful function, or the solve is a powerful function that can be used to solve simultaneous equations. So this is all there is to writing the equations for nodal analysis. One round of Kirchhoff's current law at each node, followed by one round of Ohm's law to replace each of the currents by a voltage difference divided by a resistance, and then it's just grouping like terms and then writing it as a matrix. So why don't you go ahead and tackle the example problem, and then come back and we'll talk about methods to solve a matrix problem like this.